All right, thank you very much. So I want to drill into basically the Earth and Venus in our own solar system and actually kind of look at what the potential for habitability is over time. So when we talk about habitability, it's pretty important that we actually look at the planet that we know the most about, the Earth. So what do we know about the Earth? Well, currently it's in a plate tectonic regime. It has a buffered climate, which allows for liquid water to exist over geologic timescales. However, when we look at other planets in the solar system, we see that no other planet currently has plate tectonics, liquid water, stability at the surface, or life. And this kind of leads to an implicit idea that plate tectonics is actually required for the maintenance of water and life over geologic lifetimes. And this kind of goes hand in glove with the idea of a habitable zone and liquid water from stellar luminosity. However, to add a small wrinkle to this particular idea, there's been significant evidence from geophysical and geochemical arguments that the Earth has actually transitioned lid states over time. That it started in a kind of stagnant lid or single plate planet like Mars regime, migrated through this kind of transitional or episodic lid where it's kind of alternating between extreme activity, extreme quiescence, similar to a stagnant lid, then plate tectonics, and then it migrates into a plate tectonic regime that we see today. And this is kind of a general physical idea that a lot of planets probably have the potential to evolve through. So we wanted to ask a very simple question, and that is if the Earth, through its very dynamic history, through climatic excursions, the so-called snowball Earth events or extreme glaciations, through extreme episodic transitional tectonics, alternating tectonic states, so snowballs in bluish, kind of this purple reddish, it's kind of changing tectonics, and through a variable sun, we're faint in the past, becoming more luminous with time. If the Earth remains habitable during these dynamic events, what actually is the habitability potential of kind of these episodic regimes, and specifically, what is the habitability potential of a Venus-like planet or a Venus-distant planet? And to answer this, we actually take a very simple approach, or rather to interrogate this, we take a very simple approach. We assume two self-similar planets. That is, they're both the same, they're at the same point in their evolution, surface temperatures and constituents are approximately equal. The atmosphere does not initially preclude liquid water. We do not explicitly consider a greenhouse effect. The differences between the planets then solely are that of stellar distance, time in their evolution, and solid state evolution of the planet. And we want to determine what the effects of kind of this overturn, this transitional regime is on a proxy climate system. So let's look really quickly at the anatomy of an episodic overturn. This is one overturn event. We have yielding here, gray plates are unyielded, kind of this yellow area is active yielding. Temperature plot, warm colors are hot temperatures, cool colors are cool, and when it's yielding, you have interaction with the interior. We have mobility on the top axis here. Mobility is simply surface velocity over bulk internal velocity. So a mobility of 1 means the surface moves with the mantle. This is quintessential mobile lid or plate tectonic regime. And if it's much below 1, we have relative quiescence. There's not a lot of activity at the surface. So we have an initiation phase where we go from quiescence to activity, and a recovery phase where we shut down yielding events. And the recovery phase can actually trail off for quite a bit past the initial yielding shutdown. We have internal temperatures in the mantle, mid-mantle in black, upper mantle in red. We have velocity in meters per year, and we have melt production in cubic kilometers per year. And these are all plotted versus an overturn timescale. Overturn timescale is just how long it takes a parcel to traverse the mantle. But the key points here that I want you to take away is that internal temperatures between these overturn events can invert and vary by as much as 300 Kelvin. Velocity varies by as much as an order of 100, and melt production varies by as much as an order of 1,000. Now, this is just one overturn event in a long series of overturns. So this actually is right here. What's really important here to note is that the overturns themselves, in terms of the number, amplitude, and spacing, are largely stochastic. Every model is going to be a little bit different. These are highly dynamic and disequilibrium events. So take the number, whenever someone quotes a number, take this number with a bit of a grain of salt. It's model dependent. So let's look at what the effect of outgassing is. And this is just looking at CO2 outgassing for this system. We have normalized CO2, so it's change in PCO2, plot it versus overturn time, and here are these overturn events. And this is related to volcanic flux, effectively. This is normalized to an initial state. We normalized it to its initial quiescent state to create a baseline that we have an excursion from. And kind of the key point here is the CO2 excess is always greater, the area under the curve, than the CO2 deficiency. And this has to do with the system reaching a new equilibrium point after yielding ceases. But the key point here is, and this is again just a simple outgassing model, that the CO2 excess always exceeds the CO2 deficiency. So you're always pumping significantly more CO2 into the atmosphere than you're actually withdrawing or allowing to be pulled out. But this does not actually include weathering. We can actually put a simple weathering approximation in. And to do this, we again do a normalized baseline. This is now in time and temperature, surface temperature. And we can put in a geologic scale or mantle scale weathering rate. This is not on the order of tens of years, thousands of years. This is on the order of millions, tens of millions, hundreds of millions years. And it is dependent on properties within the mantle and surface temperature and activation energy. And you can actually see that the weathering rate here, again, this is just to reiterate, it depends on viscosity of the mantle, velocity of the surface in the interior, and the temperature of the mantle, and also the surface temperature. You see during an overturn, the weathering rate ramps up really quickly as you begin to activate the surface. It kind of tails off before shutting down when yielding ceases, and you actually have a dip here. And it ceases because plate convergence itself ceases. I mean, during this, the weathering rate assumes that the mantle's moving, the surface is moving with the mantle, and that you can actually have chemical weathering occurring. Once you stop building mountains, you can't have the weathering actually affecting it. But again, the key point here is during these actual overturn events, the outgassing greatly outstrips the weathering rate. The weathering rate just simply cannot keep up. And again, outgassing, these systems will outgas significant amounts of CO2 without the ability to fully draw down, at least in this simple model. So what does this actually look like in terms of surface temperature? We have in blue our outgassing only end member, and gray this geologic mantle scale weathering modulated end member, overturn time, and change in surface temperature. And each one of these pulses, again, is that overturn event. This is the initiation of yielding, followed by the cessation of yielding. The first order shape of the curve is controlled by the yielding evolution of the system. Again, outgassing overwhelms the response of the weathering, and because or even not weathering in this case, but because outgassing actually overwhelms the system, you reset the baseline every single time you outgas. So every time you break the surface, bring material up, outgas, you're ratcheting up the surface temperature without the ability to pull it fully back down. New baseline, new baseline, new baseline, every overturn. The difference between the two models are about 12 degrees C, and the total difference, again, is 48 to 60 C. However, the number of overturns themselves are largely stochastic, so take this number with a bit of a grain of salt. So now I want to actually look at what happens kind of in the stellar evolution sense over time. And we can recast this as a zonal energy balance, where we can do surface temperature versus greenhouse forcing term, or the fraction of the long wavelength radiation emitted to space. And this is kind of a rough proxy for the planetary emissivity, at least for these models. High emissivity means you're losing a lot of heat to space, a lot of energy to space. Low emissivity, you're keeping a lot of energy. So just really crudely, you have lower PCO2, higher PCO2. And we can actually put a time evolution curve. So this is about 3.5 gigayears ago. We have two branches. We have this kind of lower branch, which is a pan-glacial state, snowball Earth, and ice-free over in this extent. And plotting an Earth-like emissivity, you actually sit pretty nicely on this pan-glacial state, this kind of snowball Earth or faint young sun paradox. And again, we can plot Earth right there. However, if we have Earth actually begin to initiate an overturn, not plate tectonics yet, but just an overturn, what can happen? And I should actually clarify, this is an Earth-like planet. It's not Earth, it's just Earth distance. As you overturn, you can actually jump to the branches and actually go to this kind of partial glaciated state. And if you have subsequent overturns, you move up the branch. If it wanes, you can actually drop back down a little bit. So you can actually start alternating between these two stable branches of your climate. For a Venus distant planet, a little bit different situation happens. You're actually moved to the left, so you're actually more in this kind of partial glaciated state. You're less likely to move to this pan-glacial state for these particular models, but again, it can wiggle either way. Kind of the key takeaways here: the early Earth would be predicted to oscillate more from very cold climates to very warm climates, so icehouse to climate conditions, where early Venus actually should have liquid water, at least initially, more likely to exist at the surface, but is also moving much closer to kind of the runaway greenhouse limit. As we let the system age, so we're now at a giga-year ago, we do the same exercise. The Earth now sits kind of in this glaciated state again, less likely to fall to this pan-glacial state. Venus gets shifted much further up now, moving very rapidly to its kind of current state of emissivity, kind of approximation to the runaway greenhouse effect. So with time, Venus gets pushed towards this runaway effect. Earth is lagging behind it. So the kind of takeaway here, which I think has been mentioned a few times during talks, is that as systems tend to get hotter, that is, the stellar luminosity increases, ice becomes much less probable and runaway becomes much more probable, even though we don't explicitly deal with it. What's kind of interesting, though, again, is just worth explicitly pointing out, is that Venus leads the way, Earth lags behind. So we're looking at kind of an evolutionary track of these terrestrial planets as the stellar luminosity increases and you're pushing kind of the edge of the habitability zone outward. So kind of the final takeaways that if you've learned nothing else from this talk, you should actually just remember these. That overturns affect surface temperature dramatically in some cases. It's punctuated extreme oscillations in terms of melt production and surface velocity. And the PCO2 production and weathering, if it exists, also will oscillate extremes. Early planets, so kind of Venus-like, Earth-like distance, will have slightly different effects. Earth distance planets will oscillate between icehouse and climate conditions. Venus distant planets actually have this greater potential for liquid water and greater potential for earlier runaway. What it means, though, is episodic habitability really is a function of time. You can drive habitability in a different lid state, but you really need to do it earlier in solar system development. And this kind of really points to the fact that we need to kind of rethink what the links between internal diagnostics of tectonic states and habitability zones. It's not just a plate tectonic argument. And there really is a pressing need to constrain the atmospheric and geologic evolution of Venus. And kind of as a final takeaway and depressing takeaway is the episodic-lid is a transitional state. Plate tectonics will end on the Earth at some point, and Venus is probably the future of the Earth much more recently much sooner than we would like it to be. And with that, I'll conclude. Thank you.
All right, we have time for about maybe one question.
Hi, what fraction of the CO2 in the mantle is degassed in a single overturn event?
That is an interesting question. So we don't actually look at the absolute magnitude, it's a relative magnitude. So each overturn event relative to its quiescent state can output 30 times to 100 times the quiescent state. So it's not, there's very likely a significant reservoir of CO2 remaining in the mantle. It's not going to deplete, if that's what you're getting at.
No, I was just asking what fraction.
So yeah, these models are just relative, so we don't actually get at the fractions themselves.